Okay, so now we're going to look at an instance where we have what's called the needle in the haystack problem. So we have this data set, which is the one I actually set for the homework. And let's just have a look at it. So we basically have, and if you can't remember what the attributes are, remember this was, I think, in the week 2 notes where I kind of printed out what all these different attributes were. They're basically financial ratios like price to earnings, you know, book value, etc., etc. And then we have a class which is, you know, whether a company's gone bankrupt or not. So actually, let's just have a look at year 4.class, and you see that of there's 1,000 companies that have not gone bankrupt and 500 companies that have gone bankrupt. So you can get more unbalanced classes than more unbalanced problems than this, but it's a little bit unbalanced. Most are zeros. Now let's just have a quick look and let's just see whether we have any missing data. So all I'm doing here is saying I'm summing if is.na, so if it is an NA, then I sum. So this is the number of pieces of missing data in my data set. What am I doing here? Well, I'm just getting the dimensions of the data set. So it's got 65 columns and 9792 rows. And I'm multiplying them together, which is the number of items, and so it's like 8,776 missing out of this huge number of data points. So we'll see we've got about 1% missing, which is not a huge amount, but it is a problem for some of these algorithms that can't cope with missing data very well. And they all cope with missing data in slightly different ways. So to make it fair, we're going to actually get the missing data. Now what we're going to use is we're going to use a pre-process function. I think this comes from Carre, but we also need an additional library here for the nearest neighbors. So this is exactly like when we did nearest neighbors classification. It basically finds if we have some missing information for an item, we kind of compare all the other items on the information that's not missing. And then we find the closest ones that do have the missing information, and then we give them the missing information from those items. So let me just kind of give you a quick example. So say we have an item here, and it's going to be, maybe would have, well, you know, let's just call it X1, X2, and X3. We won't be fancy. And we'd actually find, maybe this is 5, this is missing, and this is 4. We find another item that's very close. And we think these people are similar, and this maybe adds a 3 for X2. So we'll say this is my nearest, this is kind of my nearest neighbor. And we have lots of other, you know, lots of other guys as well, which are kind of got different values of these things. So maybe this has a 6 and a 2, but maybe a 5. This one's got maybe a a 3, and maybe it's actually a 4 as well. But this one is actually the nearest neighbor based on the other attributes. So since it's similar on other attributes, we'll consider it's a very similar thing. So we'll assign the 3 here based on this. Okay, so that's nearest neighbor imputation. It's a lot like standard imputation. You find the closest items based on the information that's not missing, and then you take the information that's missing from those closest items. Okay. So we're going to run this, and we're doing things called, basically we're pre-processing the data. We don't want to kind of do this to the actual class, which we've got, which we're actually full. And we're running this k-nearest neighbors imputation. K-nearest neighbors is like one method of imputing the data. And so we basically run it to get how this defines the imputation, and then we predict, we send it the data set, and it will get the new data set. So this actually might take a few minutes, so I'll just stop the video. Okay, so now we have the new data that's been basically imputed. This shouldn't have any missing data in it. Let's just kind of quickly view it. Now notice that these numbers are now all basically standardized. They've had the mean subtracted and then divided by the standard deviation. This is because the k-nearest neighborhood works on distances. So that to kind of calculate distances between items, all the attributes need to be kind of pretty much on the same scale. So we can see here, and these are kind of the imputed values for each of the items. Okay, so let's kind of go back. We've got our data. And all we're doing now is we're just going to kind of combine it with the new data with the class labels. And we're going to do what we did before. So we're going to go 100 runs. We're going to split it into training data and test data. We're going to do the now we're actually, because we did the k-nearest neighbors imputation, we can actually do k-nearest neighbors very easily. So we can do the k-nearest neighbors as we did before. We can do the logistic regression, where we predict the class, whether it's bankrupt or not. And we're going to do the linear discriminant analysis. So we're going to run the 3 of these, and for each of these, what we're going to do is we're going to calculate, the classification table, and for each run, we're going to add the classification table. So all this is doing, say if we only have one run, then if we're on the first run, we create the classification table. If we're on subsequent runs, we add it to the existing classification table. And at the end, we basically divide by the number of runs. So let's make sure we have all that loop on. Okay, this is doing 100 runs on quite a large data set. So again, I'm just going to, maybe this might take a minute or two, so I'm just going to pause it. Okay, so we now have the data, and let's just have a quick look at the data. So let's just kind of have a look at our tables. As I said, what we're going to do is we're going to divide the tables by the total in the tables, which just gives us the remainder proportions, and we're just going to change them into percentages. So let's just kind of have a look at each of these tables. Now what we're doing here is we're looking at the kind of the average table. This looks fancy, but all I'm doing is I'm taking the sum on the diagonals, i.e. the false, false, true, trues, divided by the total sum. So this is just giving me the accuracy from the tables. So let's just have a look at my 3 methods: k-nearest neighbors, logistic regression, and linear discriminant analysis. The overall accuracy looks good. I'm like, whoa, 95%. I'm really good at this analytics thing. But then you actually look. So of the zeros, we've correctly classified this amount, and we've not correctly classified this. So we're doing really well with the zeros, but with the ones, we still have most of those classified as zeros, the bankrupt companies. So we're actually doing very well overall, but it's mostly because just everything that's not bankrupt we're saying is not bankrupt. And we're not doing very well at classifying the bankrupt companies, which is kind of what we wanted to do in the first place. So the idea behind this is it's always going to be really difficult to predict a minority class. It's a very difficult problem. And we probably need a new way of measuring it. So I'm now going to go over two kind of concepts on the whiteboard. That's going to be of measuring classification performance using lift, percentile lift or decile lift, and also this idea of under and over sampling. Okay, so let me just get my... Okay, so the first thing we're going to do is we're going to have this idea of oversampling. So imagine, and let's just kind of imagine that we have our data set. I'm just going to draw it in a bucket. So this is my original sample data. And it's got some red items. And it's got some blue items. And let's just say, imagine that we have 20% red, 80% blue. So there's kind of a ratio of 1 red to every 4 blues. And what we want to do is we're going to take a new data set, we're going to resample. So this means we're going to, and the statistics is probably a little bit beyond this course, we're going to use something called an EM algorithm or maximization algorithm. But basically all it means is we're going to take we're going to try and sample very similar items from the data that we already have. And what we want is we want a sample that's kind of 50% red, and 15% blue. So let's just make, oh, I'm making it bluer and bluer. So there we go. We now have this sample that's 50%, 50% red, and 50% blue. And, we basically have to, here, to get to 1-to-1, we have 100%, and we'd need to oversample another 300% in order to make the reds similar to blue. So all we're doing here is we're oversampling this minority class. So we're going to oversample the minority class. Okay, so the second little concept is that of the percentile lift. And just to avoid making it too complicated, I will actually just go with the decile lift, which is the percentile lift with 10%. So what we're doing here is we're going to predict bankruptcy. And we're going to use something like, say, logistic regression, e.g. logistic regression will give us a probability. We'd have probability bankrupt, so probability of 1. And that's the probability of it going bankrupt, say something, whatever. So what we do is we have maybe 100 items. In the test data set. And we kind of order them in terms of the probability. So the first one is going to be the highest probability. So let's just say this is probability of 99. So we have the probability. So this will be minus 9.9, then minus 9.7, etc. Okay, so we had something of a technical error, so I had to kind of reboot my computer. But the idea is we're basically ordering all of our items in terms of the probability of a success, which we're predicting on the test data set. So imagine that the item that we predict has the highest chance of a bankruptcy, we kind of label as 1. So maybe we predict this has got a 0.99 probability of bankruptcy. And then we order all the items in order from the ones we think of, the highest probability of bankruptcy to the lower probability of bankruptcy. Then what we do is we take the top 10% and then we note the classes of each of these items. So here, red is a bankruptcy and blue is a non-bankruptcy. So what we're going to do here is we find the top 10% and imagine here that the proportion of bankrupt is, say, 50% equals 0.5. And imagine in the overall data set, so the overall data set the proportion of bankrupt equals 0.1. Then our decile lift is basically just the proportion bankrupt in which of the top 10% which we predict will go bankrupt over the proportion bankrupt in the entire data set. So it's basically how much of the ones we think are really going to go bankrupt, how much improvement do we have over average? And in this case, it's going to be 5. So our decile list is going to be 5. So this is a nice way, because you get depressed when you have this like needle in the haystack problem, when you only have a few success classes. It's very hard to kind of get your recall over like 0.5, and it gets a bit depressing. But what you can say is, hey, I've done 5 times better than average, which is a good thing. Okay, so let's kind of return now to our data set. I'm looking at this now. And we're going to actually start off by looking at, we've just talked about oversampling. We're going to implement an oversampling technique called smoked, which is in this library. We can actually get it from the table. And let's just think what we need to actually pass to it. So we need to pass it pretty much what we would do for regression. So the dependent variable is the actual class for prediction, and then the independent variables are all the other variables, name of the data set. And what we're doing is we can either oversample or we can undersample. We're just going to focus on oversampling for this class. So undersampling means we undersample the majority class. Here we're oversampling the minority class. Now what am I doing here? Well, the Y summary, let's just have a look at this. This means we have 515 bankrupt companies and 9,277 non-bankrupt companies. So we want to find the ratio. And let's just have a look at this ratio. Oops. That's about 18 to 1. Now we want to work out how much we want to oversample. We don't want the original data. We want to see how much above that is. So we just subtract 1 from the ratio. And our oversampling, we want to oversample about 1700%. So we define that. We run smoked and we create a new data set. And we see that now it's a little bit different, but we're roughly even between bankrupt companies and non-bankrupt companies. So we can utilize this. So what we're going to do now, let's try and run some methods. So let's do what we did before. But this time, we're going to create test and train data. But we're also going to create training smoked data. So basically we create a resampled class with balanced, bankrupt and non-bankrupt. So we're just basically creating we're creating a balanced training data set. The test data, of course, is the same because we still eventually have to predict on this unbalanced data. But we're hoping by getting more bankrupt companies into our training data set, we actually build a better model. And so we're going to do exactly what we did before. We're going to fit the logistic regression, linear discriminant analysis. We're going to fit the tree. And now we're going to do it also on the smoted data set, on trained data too. So let's just run all of this code. And what we're going to do is we're now going to calculate the percentile lift. So what I mentioned before, I actually created a function to calculate the percentile lift. And let's run it. And this might take a while. So we're basically, for each of the different runs, we're calculating the percentile lift. And then we're going to kind of aggregate all of these at the end. So I'll just pause the video while this runs. Okay, so let's see what our results are with respect to decile lift. And you can see that we're actually, doing quite a bit better than randomly. Linear discriminant analysis seems to be the best performing method, followed by the tree technique, and then followed by poor old logistic regression in third place. And basically, for the logistic regression and the LDA, the smoting of the data set seems to help, but it actually seems to have a negative effect for the tree data set. We can also have a look at the, for example, for the last run, we could also kind of have a quick look at our tables. And we actually find out how well we're doing. And it's kind of interesting. Let's just have a look at what we did pretty well on linear discriminant analysis. And you can see, for example, that obviously when it comes to zeros, we're actually doing pretty well. We're getting most of those in the zero category. But again, we're predicting a lot more ones as zeros than we are as ones. But in fact, in terms of the decile lift, we're probably doing about 3 times better than average. Okay, now you're looking at all that code and thinking, whoa, this is getting more and more complicated. We're doing lots of runs, we're comparing lots of techniques. So what I did is I created 2 different functions for comparing methods. And this basically goes through all the methods we've done and a few more. Now what you need to do, the important thing with these functions I created, these are in the analytics aid. There's basic cross-validation and Carré cross-validation. You need to have all your independent variables to the left, and the last column of your data set needs to be the dependent variable, which happens to be, for this bankruptcy, this is how it was. But importantly, your dependent variable needs to be called y. So the name of the dependent variable is y. So here we put col names for our last column, our dependent variable is y. The basic cross-validation just does what I've been building up manually. So it kind of does a more complicated version of this. You pass it the value for success. So in this case, the bankruptcy, the 1, is a success. You kind of run it 5 times, and 10%, this is the percentile, you have decile lift. Now, for the Carré cross-validation, remember it gives slightly different output. So we run it, this is the number of folds. So here we're doing 10-fold cross-validation, i.e. each test data set is a 10th of the original data set. And we're going to run it 5 times. So again, I'll pause the video and show you the results of that. Okay, so let's have a quick look at what the basic cross-validation has given us. So that's given us basically both the accuracy and the decile lift. So you can see here that we have 2 techniques, and I'll explain those a little bit kind of in the next few weeks. We've got random forests, and what a random forest is just a kind of a bunch of trees. It combines lots of different decision trees, and trees make a forest. And the idea is that, one tree gives a decent prediction, but if you combine the predictions from lots of trees, then you can actually get an even better prediction. So we see here that the random forest gets a decile lift of over 4. And see, there's an additional technique added. This is called adder boost. And again, this is another method for combining lots of different individual techniques. These are called ensemble techniques. And you'll see the accuracy is a little bit different. And it's hard to get to see what the accuracy is here. You know, the tree actually gets the best accuracy here, but it might just be kind of predicting zeros all the time. And then next, we actually have the caret cross validation. And I didn't want to do that because I've already done it. So we have the caret cross validation. And we get those caret, we get the kind of the accuracy adjusted for random error. And you see we have very high accuracy, but just randomly selecting we get high accuracy. And you get the different methods. We've got 6 methods here. And you can see how well they do adjusted for random error. And in this case, the linear discriminant analysis with SMOTE actually does the best. So just to finish off, when you start your project, a good way to start it off, get your data, do a little bit of exploratory analysis, then kind of run some individual techniques and try to understand your problem using those techniques, i.e. the parameters of the logistic regression or the actual trees created by your tree techniques. And then you can actually look at predictive power starting off with these 2 functions. Okay, and that's it for this week.